Hey everyone, welcome back to Abstract Algebra 1. This will be lecture 4 of the course, and in this section we're going to define the group concept from algebra and get into some of the elementary properties of groups. So let's go ahead and jump into it. And we'll call this section 2.2 Group Definition and Elementary Properties. Okay. So, obviously, so the term group, it didn't, when it was initially used, was not fully flushed out as per anything that is new. And I think it was initially used to describe one-to-one functions, certain sets of one-to-one functions. And these were sets that I believe the concept was they could be grouped together to form a closed set. So the idea of closure was there from the beginning. It's gone through many alterations since then. It's been enlarged and refined as anything in mathematics. Same kind of treatment that anything gets in mathematics. And so in this section, we're going to define sort of the current understanding of what a group is, and we're going to see a lot of examples. Okay, we're going to see a lot of examples. Okay, and we're going to start, before we get into the group definition, we do need a couple of things up front. So one of the things we need is the definition of a binary operation. This will be intuitive to most people, but let's get it flushed out and level set on this. Binary operation. A binary operation. We're going to let G be a set. Okay. A binary operation on G is a function that assigns each ordered pair of elements of G another element of G. So it's a function that assigns each ordered pair of elements of G an element of G. There are different ways to define binary operation. This is one such way. Okay, examples of binary operations. Right, we've seen these basically since you've been doing math from kindergarten, right? So regular arithmetic operations plus, addition, subtraction, and multiplication of integers. These are binary operations, right? So if you think about it, like if you've got a and b integers, then multiplying a and b gets you an integer. Adding a and b is another integer. And subtracting a from b or b from a gets you an integer as well. Right, so in this case, we exclude division, right, the fourth arithmetic operation, but you can imagine that in the case of integers, if I divide 5 by 3, 5 divided by 3, I don't get another integer, right? And so in our context, binary operation means that if I do the operation on elements of G, then the result is an element of G, right? The function maps an ordered pair of integers to another integer, right? In the case of division, that can't be guaranteed. Okay. Right. And so, just take it a little bit further. If I take the two integers 10 and 2, well, clearly 10 times 2 is 20, which is an integer. 10 plus 2 equals 12, which is an integer. 10 minus 2 is 8, which is an integer, right? So this is an example of a binary operation. But 10 divided by 2, well, in this case, it would be an integer. But another example is something like addition modulo n. Okay, so if I have like 5 mod 7 for 5 mod 7, we know that that's equal to 5. 20 mod 7 is, well, let's see, so that'd be 6, right? right? 7 times 2 is 14, plus 6 is 20, right? And so if you think about what this looks like, it'd be 0, 1, 2, 3, 4, 5, 6. And so this is mod 7. So anything done modulo 7 ought to return one of these elements, 0 through 6, right? And indeed, that's what happens, right? So 5 mod 7 plus 20 mod 7 is the same as 5 plus 6, which is equal to mod 7, which is equal to 11 mod 7, which is equal to 4, right? So I get something in the set. Okay. So take two things in the set, I get something in the set. So it's a binary operation. Okay. Very good. Okay, let's see. Yeah, so that's the idea of a binary operation. Okay, so let's take a look at the definition of a group. Okay, so let's get into the definition of a group. Okay, we're going to let G be a non-empty set, right, together with a binary operation. Together with a binary operation. And the binary operation is going to assign each ordered pair that assigns each ordered pair AB of elements in G. Okay. And we're going to denote this assignment as AB. Okay. Okay, so we're going to let G be a non-empty set together with a binary operation that assigns each ordered pair AB of elements in G, denoted AB. Okay, well, let me write this a little differently. Denoted AB, right? So when I combine A and B via this binary operation, the new element I get, we're gonna write it as AB. Okay. So we say G is a group under this operation if the following, right? So there's a couple things, and we talked about all of these in the last lecture. The first one is associativity, right? So A, B, C equals A times BC. Okay, we'll write it like this, right? And this is obviously for all A, B, C, and G. Okay, right? So this binary operation has to be associative, right? So the how I associate the operation shouldn't make any difference. Okay, associativity. The second requirement for a group is that there needs to exist an element. We'll denote it with an E. There needs to be an element in G. We'll denote as E, such that A times E equals E times A equals A for all A and G. Right? And this is the identity element. Okay, so there's an identity. So this is associativity. And then down here I've got identity. Right, so you remember with the dihedral group, R90 and an R90 and an R270 produce the identity. Right, or better, I guess better way to say it would be that anything composed with R0, the identity element, resulted in a return to the original element. And that's the identity element. Okay, and then the third thing that's required here is that for all A and G, for every element in G, there exists a B in G, okay, such that AB equals BA equals E. Okay, and this is the inverse property. Okay, so for every element in the group, there needs to be another element in the group such that when I combine them, I get the identity element. All right. So we saw this with the dihedral group. We have, for example, R90 and R270 are inverses of one another. Because when you compose them, you get R0, right? A vertical flip and another vertical flip are inverses of one another, right? Because when you compose them, you get back to the original R0. Okay, and so these are the three properties that make up a group. So if you think about what a group is, then a group is basically a set and some operation on that set that fulfills these three requirements, right? The operation needs to be associative. We must have an identity element somewhere in the group, and the elements of the group have to all have an inverse, right? Meaning that when you multiply it with some other element in the group, you get the identity element. Very simple definition, right? Pretty easy, pretty simple, easy to remember. Identity, inverse, one group, or sorry, a set, a single operation, identity elements, inverse elements, identity element, singular, inverse elements, and associativity of the operation in the group. Okay. Okay. All right. Very good. Let's take a look at some examples here. One second. Let me check something here. Yeah. And then I guess kind of written into this definition, I do need to point this out, is that the binary operation, which combines A and B, the new element, the element that's mapped to, is a binary operation. So as the way we've defined binary operation, that means that AB is in the group, right? And so closure is here as well, right? So just, it's kind of behind the scenes, but let's make sure that we're clear on that. When you take any two elements in the group and you combine them, you get a third element that's in the group, right? And that means closure. Okay, so that's sort of in the background here a little bit. So G is a non-empty set together with a binary operation. That binary operation we just defined takes two elements from the group and assigns it to a third element in the group. So you have closure as well. Okay. Okay, very good. Now, just to add on to this real quick, let's point out this idea. Where does commutativity come in? So if G is a group, and AB equals BA for all AB in the group, then G is called an abelian group. Abelian group. Okay, right. Abelian group means commutative group, right? It means every element in the set G commutes under whatever the binary operation that the group status comes from. All right. So if you have every element commuting, then it's called an abelian group. And I'll just put here or commutative group. Right, and this name abelian is based on probably the founder of group theory, which is Niels Abel, A-B-E-L. And so abelian groups are named in his honor. If a group is not abelian, then it's called a non-abelian So non-abelian. There you go. And or you could say non-commutative group. So okay, all right, very good. So that's the formal definition of a group. Okay, so let's talk through, now that we know kind of what, we have a sense for what a group is, let's try to build some good intuition, right, so that we can recognize a group when we see it, because we'll have some good examples in our head. Okay, so as soon as you get a definition, the first thing you should seek is an example. Okay, and here's your example, right? So we'll do lots of examples. Here's the first example. The dihedral group of order 4. Dihedral group of order 8, sorry, is a group under composition. Okay. The elements of the group we saw, we had R0, R90, so rotations, 0 degrees, 90 degrees, R180, R270, and then we had the flips and the just the flips basically, the horizontal flip, the diagonal flip, the other diagonal flip, and the vertical flip. Right, so those 8 elements there, and conjoined with the idea of a composition of motions, gives you the dihedral group that we talked through in the previous lecture. So if you haven't watched that lecture, if you skipped over it, then you should go back and watch it and be thinking of how the definition of a group is met by that physical mathematical structure that we've talked through. Okay, so that's an example we've seen, and here just pointing it out. Another example would be, here's a trio of examples. The integers under addition are a group. The real numbers under addition are a group. And the rational numbers under addition is a group. So these are all groups. Okay, they're all groups. So this is the notation you'll sometimes see, the name of the set and then the operation indicated, kind of like this in a pair. So integers under addition are a group. Let's verify it for the integers. Let's verify that the integers under addition are a group. Okay, so let's talk through the principles. Associative. Okay, so associative. Right, so A, B, and C integers. Then, there's not much to do here. We know this is the case. Right, this is definitely true for integers. Right, this is just this is true by the ordinary properties of arithmetic. Just the ordinary properties of arithmetic. Right, so we've seen this since grade school. Right, we know that 2 plus 3 plus 5 is equal to 2 plus 3 plus 5. We know that's true. Okay. What about the identity? Is there an identity in this group? Yeah, definitely, right? 0 is an integer. 0 is the identity, right? A plus 0 equals 0 plus A, which is equal to A for basically in every integer, for all A in Z, all integers. Okay. What about inverses? Okay. Well, let's let A be an integer. Then there always exists negative A, an integer, right? And if you have A and negative A, you get the identity when you combine them under the binary operation of addition. right? So a plus negative a is 0, and obviously negative a plus a is 0 as well. Right, so 5 plus negative 5 gets you the identity element of 0. So every integer has an inverse. Right, what's the inverse of negative 10? Well, the inverse is negative 10, which is positive 10. Okay. Now, this is also an abelian group. All three of these actually are. So the integers under addition is an abelian group. And it's abelian because a plus b equals b plus a for all a, b integers. So it doesn't matter the order, right? You can change the order. It's true for real numbers and for rational numbers as well under addition. Okay. Now, this is an example of a group, but notice that if we change the binary operation here, z together with multiplication is not a group. All right, so sometimes it's good to see the counterexamples too. Now, associativity works, right? A times b times c equals a times b times c. If we're talking integers here, this is fine. Identity element works, right? We have the number 1 as an identity. Anything times 1 is itself. So a times 1 equals 1 times a equals a. But the elements of the integers do not have an inverse under multiplication, right? There are no inverses under multiplication, right? So an example would be like if I take the integer 10, there does not exist a integer such that 10 times a equals 1. Right? I mean, the key here is to notice that 1/10 is not an integer. Right? So there's no integer that I can call on to create this inverse. Okay. All right. Very good. So those are this is kind of an elementary sort of example. You know, the integers, real numbers and rational numbers under addition. Okay, let's take a look at something a little less elementary. And let's consider M2 under addition. So here M2 is 2 by 2 matrix. Okay, and we're saying M2 here is 2 by 2 matrices with just real entries, real valued entries. Okay, so we're going to let A, B, C, D be an element of M2. We want to show that this is a group under just matrix addition. So is it associative? Well, so that means A, let's see here. Yeah. A, B, C, D plus E, F, G, H. Okay, equals, and then plus I, J, K, L. Right, so if I add these all up, right, does it matter if I do these two first? Well, let's try it. A, B, C, D plus, and then it's E plus I, F plus J, G plus K, H plus L. Okay, and then I add it together again. A plus E plus I, B plus F plus J, C plus G plus K, and then D plus H plus L. Okay, now you can see that I'm going to get the same answer if I do the first two matrices, and I'll just leave that to you to verify. Right, so you can verify that. This is an F, sorry. Weird thing at the top there. So yeah, so you can verify that you get the same thing. So associativity is fine. What about the identity? Is there an identity element in this group? What would the identity element be? Well, E in this case would be 0, 0, 0, 0, the zero matrix, right? Right, and it's clear that A, B, C, D plus 0, 0, 0, 0 equals A plus 0, B plus 0, C plus 0, D plus 0, right? So it's just A, B, C, D. Right, and then of course the order, you know, doesn't matter. Here I could do 0 plus A, right? This is addition, right? Just adding the elements, it doesn't matter the order in which you add them. Okay, so you've got an identity element as 0, 0, 0, 0, right? This guy here. What about inverses? Yeah, you've got inverses too. So A, B, C, D, the inverse of that is negative A, negative B, negative C, negative D. Right, and that's because A, B, C, D plus negative A, negative B, negative C, negative D equals A minus A, B minus B, C minus C, D minus D, or 0, 0, 0, 0. Right, so you get the identity element when you add this inverse to its inverse. Okay, and so, you know, the 2 by 2 matrices under addition. Geesh. M2 under addition is a group. Now, important, I'm not proving closure here, but if you have some questions over closure, you should double check it. Right, now if I add it together any two 2 by 2 matrices, do I get a 2 by 2 matrix? Yes, right? So in the background, you should always double check, make sure you have closure. And, you know, some textbooks emphasize closure more than others. The one I'm working from obviously doesn't. They kind of bake the closure into the binary operation, right? So just keep in mind you always want to make sure that your operation is closed, right? And so closure is here. And so I'll just write that up here. A, B, C, D plus E, F, G, H. That sum is always in M2. Yeah, you're never gonna. In this case, there's no way to add 2 by 2 matrices and get something else. Okay, so that's good. So we've got that as well. Kind of in the background, I want to make sure that you want to be thinking about that up front, because frequently groups will go awry because the operation they're not closed and they're under the operation. So here's an example, another kind of somewhat more unorthodox example. The set, and I'm going to denote it as R star, and this is going to be the non-zero real numbers. The non-zero real numbers. So this set, the set R star of non-zero real numbers, is a group under multiplication. Right, so that's a group under multiplication. Right, the identity is 1. Just like what we saw with the integers, we kind of went through this example with the integers. Associativity is fine. We had an identity. Associativity works with multiplication. The identity is 1. But in the case of the integers, the group definition fell short because we didn't have inverses. But we do have inverses in this set, right? So for all a and r star, 1 over a is the inverse. Right? So here we have not just integers, right? So here we are extending into the rational numbers as well. Right? So any number in R, I can identify the reciprocal of it, and that's the inverse of that's the inverse, right? So you have inverses now, and so R star with multiplication is a group, right? Now 0 can't be in the group because 0 does not have an inverse. There's nothing I can multiply against 0 with. So 0 is excluded. Because there is no multiplicative inverse. Right? Namely, there does not exist a in R star such that 0 times a equals 1. Right? That's not going to work out, right? Anything times 0 must be 0. Okay? So that's why the real numbers have to exclude 0 in order to work with this group definition. All right, very good. Let's see another example. Examples are the best thing to look at when you're getting started with abstract algebra. You just want to have a good stockpile of things to draw on. How about this one? The integers and subtraction. This is not a group. Okay, so first of all, there's a problem with the associativity, right? So C minus A minus B is not equal to C minus A minus B in general. So associativity fails. Right, so it'd be really easy to go find an example, right? 10 minus 2 minus, here, let's do it. 10 minus 2 minus 5. That's going to equal 10 minus negative 3, which is 13. But 10 minus 2 minus 5, that equals 8 minus 5, which is 3. So associativity fails, right? We don't even need to look at the other operations, right? If you don't have associativity, then you don't have a group. Okay, how about this example? This is going to look familiar if you've taken linear algebra. Rn, right? This would be the set of n tuples or vectors of length n. So a1, a2, dot, 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 an, such that ai, the entries of the vectors, are real numbers. So this is a group under component addition. All right, so if I just add vectors together, I get a group. Associativity is straightforward, right? You can do that one yourself. Just check it. Associativity is straightforward. What about, what's the identity element? Well, it's just the 0 vector. Right, and then inverses are just negative a1, negative a2, negative an. Right, and so you can obviously confirm that if I take a1 through an and I add to that negative a1 through negative an, then I obviously get the identity element out. Okay, and then of course closure, right? Adding n vectors together always results in an n vector. It's not like you're going to get to an n plus 1 vector or something like that, or a constant. You're always going to get n vectors, right? And so the set is closed. Closure is there. Okay, very good, very good. Let's take a kind of a tricky example here. Let's do a tricky example. The set, and we're going to denote it GL 2, comma R. This is the set of 2 by 2 real matrices. It's a set of 2 by 2 real matrices with non-zero determinants. Okay. The GL here stands for general linear. Okay, so general linear. So these are just 2 by 2 matrices with real valued entries, but these matrices all have a special property that their determinant is non-zero. Right, and so let's write this out a little bit more concisely. GL 2R. This is equal to the set A, B, C, D matrices of that form, where A, B, C, D are real numbers, and the determinant, which in a 2 by 2 matrix can be calculated as AD minus BC. That's not the determinant, but it's part of the calculation of the determinant. That piece of it has to be non-zero. Now, it turns out that this set of special matrices is a group under matrix multiplication. This set is a group under matrix multiplication. Okay, so matrix multiplication, if you remember, is a little bit cumbersome, right? So you'll have hopefully been through linear algebra, you'll have seen it, and you should take the time to confirm that associativity works. Okay, associativity can be verified. The thing to notice here is that it's not that it's hard to verify this, it's just tedious. Right, you got to basically do a bunch of multiplication. Right, it's basically just going to have to multiply this all out, but it can be done. It's a little cumbersome, but it can be done. I'm not going to do it because it's straightforward if you remember how to multiply matrices. So that's associativity, right? And I guess we should say that this is obviously going to be closed, right? If I take any two by 2 matrices, right? A 2 by 2 matrix multiplied by a 2 by 2 matrix gets me a 2 by 2 matrix, right? So just to keep that in mind, that if you think about the dimensions that are required to do multiplication, you have to align on the inner two, but then the resulting matrix will be the outer 2 dimensions, and so 2 by 2 by a 2 by 2 will be a 2 by 2. So it's closed, right? Now, what we haven't shown is that by necessity the product will have a non-zero determinant, but you're certainly going to get a 2 by 2 matrix. Let's talk about the identity and other items first, though. Okay, so the identity, what would the identity be? Well, the identity is the identity matrix, 1, 0, 0, 1. Okay, and the inverse, right? The inverse of A, B, C, D, and I'll leave it to you guys to kind of look at why this might be the case, but it is actually D over AD minus BC, and then negative B over AD minus BC, and negative C, AD minus BC, and then A over AD minus BC. So this matrix here is the inverse of A, B, C, D, right? And so this obviously is how you can see that, why you can see that the AD minus BC is non-zero, right? Because you have to divide, right? In order for the inverses to exist, then this AD minus BC has to be non-zero. Okay, so that's that. And I think I'll leave it as an exercise to you guys to go and try to figure out how it is that two matrices with non-zero determinant will yield a third matrix with non-zero determinant. The product will yield a third matrix with non-zero determinant. So go try to figure that out. Actually, it can be proven just using linear algebra. You don't even have to expand it, but see if you can figure that one out. Okay, very good. So that's a lot of examples we've gone through, tons of examples. What I want to do next is I want to get into some of the elementary properties of groups. And so some of these we've hinted at. I want to be a little more thorough. I want to do a little more thorough treatment of some of these guys. Elementary properties of groups. And so the first one that I've hinted at, but we've definitely not demonstrated, is that in a group G, there is only one identity element. Okay, there's only one identity element. There aren't two of them, there's only one. Okay, and this can be shown just by a nice little logical little argument here. All right, so let's let E and E prime be identities in G. Okay, then, well, first thing is that if E is an identity, then A times E equals A for all A and G. Okay, and second, E prime times A equals A for all A and G. Right now we know that if E and E prime are identities, then they commute with every element, but I'm just choosing to write out these versions. Okay, so then from 1, let's see, if we let A equal E prime, we can see that E prime A equals A implies E prime E equals E, right? So letting A equal E prime, just let A be this other element E prime, right? Then E prime A equals A implies that E prime E equals E, right? So that's not a problem. And now from 2, we can do something similar. From 2, if we let A equal E, if we let A equal E, we can see that what? Well, we can see that E prime, E prime A. Oh shoot, I did this wrong, darn it. I'm sorry, I want to redo this section. I wrote it wrong. So from 1, first we let A equal E prime. Okay, so let A equal E prime. Then we have A times E equals A, and that implies that E prime E equals E prime. Okay, sorry about that. So, right, again, just it's the same thing. So here instead of A, we're plugging in E prime. So E prime is another element in the set, and so it should have an inverse as well, and the identity, or sorry, it should work with the identities as well, right? So you get E prime E equals E prime. And now secondarily, let's let A equal E, right? So those are two different things, so we can assign them at the same time. So A is equal to E prime, A is equal to E. So then we would have E prime times A equals A, and that implies that E prime times E equals E, right? Okay. Okay, so then this is, then what do we have? We have E prime E equals E prime, and E prime E equals E. Okay, and what does that mean? Well, E prime times E is E prime, right? So these two are the same, right? So E prime and E are the same. That's the whole point there. Right, so this is, I guess, a little, I might have like not presented it in the most itemized and precise way, but be careful when you go through this. But the idea is that, look, you can just set A equal to E prime and derive this lickety-split. You can set A equal to E and derive this lickety-split. The two point out that the two taken together imply automatically that these two identity elements must be the same. They have to equal one another. Okay, so the identity must be unique. If E prime equals E, then the identities are unique. Okay, that's fine. That follows. Okay. Let's see. Another thing to point out, fundamental properties, elementary properties, would be in a group G, the right and left cancellation laws hold. Okay, so the cancellation laws hold, right? So for example, if I have B times A equals C times A, then that implies, and the way you think about it is like, well, I can cancel A here, right? That implies that B equals C, right? And similarly, A times B equals A times C implies that B equals C, right? The A's would cancel. Right, and we can show this one as well. This is got a simple proof. So let's let BA equals CA, and let's let A prime be the inverse of A. Okay. Well, then I could just say BA times A inverse equals CA times A inverse. And I can reassociate, and B and then AA inverse equals C times AA inverse, like so. And that, of course, is B times E equals C times E, and then that is B equals C. So basically, like, this left and right cancellation works because of the existence of the inverses. I can always multiply on the left or the right by the inverse on both sides of an equation like this, and you can get that the cancellation laws work. So when you see this kind of thing here, it's safe, if it's a group, it's safe to just disregard the A's and to equate B and C, if it's a group. If it's not a group, it may not be safe to do that. Okay, very good. Another kind of elementary property here is that for each A and G, there's going to exist a unique B in G such that AB equals BA equals E. So this is the uniqueness of the inverses. For each A in the group, there exists a unique B in the group such that AB equals BA equals E. This is a nice, very quick one to show. Suppose you have two different inverses for A. So suppose B and C are both inverses of A. Okay, then, well, AB equals E and AC C equals E. Okay. So then you can equate these two. AB must equal AC. And we just talked about the cancellation laws. That automatically implies that B equals C. So there you go. If you have inverses, they must be equal. Now, we're going to kind of get straight on some of the notation here. So we'll typically denote the inverse of an element with inverses are typically denoted with A inverse, or in some cases, like what we did up above, A with the prime, but usually with the inverse. Right? Usually this is the preferred notation. Okay, now this notation obviously comes from real numbers and multiplication, right? And just exponentiation in general, right? So this is going to come from exponents and be like the things we're used to, right? So for inverses, we'll use A inverse a lot, most of the time. This notation, yeah, so again, it comes from real numbers, right? So we have this kind of a setup here where we use the exponent here to denote n items in the product here, right? And then we also have seen notation like this: a to the 0 is equal to e. Okay. Now when n is negative, right, when n is negative, we usually say, what do we say? We say a to the n, negative n, equals a to the negative 1 power to the nth. And here the absolute value. So for example, g to the negative 3rd power is equal to g to the negative 1st power cubed, right? And that all works out arithmetically. So this notation is really nice because it works with all of the familiar laws of exponents. All right, so this notation is nice because it works with all the familiar laws of exponents. Right, so for example, a to the m times a to the n equals a to the m plus n. And a to the m to the nth power is a to the m times n. Okay, but keep in mind that ab to the nth power is not equal to a to the n, b to the n in general. Now, when do we have to be careful with this notation? We really have to be, this notation can get a little bit, this notation works great when we're talking about multiplicative groups, right? Groups where the binary operation is basically multiplication. But it can get a little tricky or confusing when we're dealing with additive groups. Okay, so that's when we have to be really careful, is when we're dealing with additive groups. So we have to be careful when dealing with additive groups. Right, so for example, sorry about that. So for example, g plus g plus g equals 3g, right? So here I'm adding elements in a group. So it would be notated as g3 if the group were multiplicative. Okay. And also, like, g to the negative 3, right? That, would mean, in the case of an additive group, would mean negative g plus negative g plus negative g, right, in an additive group. Right, but this is obviously better notated as negative 3t. Negative 3g, right? Okay, so that is something to note, right? But in general, like we'll very often, if the group is multiplicative, we'll very often utilize the notation of this, like this, for inverses, right? And just in general, exponentiation makes a lot of sense in multiplicative groups. It gets a little hairy when we're looking at groups where the operation is fundamentally additive. Okay, perfect. All right, so that's where I think we'll end it. There'll be more to come, obviously. So we've gone through the definition of a group in this section, and we did a ton of examples, a bunch of examples. And and then we talked through some of the more elementary properties. So the uniqueness of inverses, the uniqueness of the identity elements, left and right cancellation, right? And so that's where I think that's where we'll leave off. And when we come back next time, we'll talk more about group properties. We'll get into finite groups, and then we'll also begin to discuss what are called subgroups. So like a subset, but a subgroup. So it's a subset of the group, but you still have all of the niceties. It's a group in and of itself. It's kind of like a subspace if you've been through linear algebra. Similar idea. All right, so we'll leave it there, and we will talk to you all next time. Take care.